Finishing up our discussion of equilibrium, we'll hit what's called the additional aspects of aqueous equilibrium, which is kind of a catch-all for the other topics that we want to include in our discussion of equilibrium. So we'll start out by talking about common ion effect. We'll get into buffer solutions, acid-base titrations, solubility equilibria, factors that affect solubility, and we'll talk just real briefly about the last two sections dealing with separation of ions and quantitative analysis. So the easiest way to look at the common ion effect is to just do a couple of sample problems. So the first one says to determine the pH of a 0.5 liter solution of 1.0 molar HCN after the addition of 24.5 grams of sodium cyanide. So what we've got here is a weak acid, the HCN, but to that we're adding sodium cyanide. So what we want to do is take a look at what the sodium cyanide is going to do. So sodium cyanide is NaCN. All right, you see that I've strategically chosen to add 24.5 grams of it, and the formula mass is 49. So we're actually adding 0.500 moles of the sodium cyanide. Now, being an ionic substance and the fact that the metal ion is an alkaline metal, this is soluble to a great extent in water. So instead of really having sodium cyanide, what we really want to be thinking of is that we've got sodium ion and we have cyanide ion in solution. Now let's take a look at our acid equilibrium that's occurring. So we've got HCN, and we'll use the shortened form of our expression. So here's our acid equilibrium that's occurring, and of course we know the molarity of the solution. It's a 1.0 molar solution, so we can do the equilibrium, acid-base equilibrium expression here, but taking into account that we're going to have some sodium ion present from the sodium cyanide that was added. So let's go ahead and set up that chart. So here we have our chart, and we've got our initial, our change, our equilibrium, HCN, H plus, CN minus. Our HCN concentration, according to the problem, was 1.0 molar. Our H plus concentration, we're going to say is 0. And our cyanide concentration, we have 0.5 moles. 0.5 moles per 0.5 liters of solution, which gives us a molarity of 1.0 molar of the CN minus. Let's move this down. Well, obviously, since we have no H plus in this, we're going to be shifting to the right. So the HCN will go down by x, H plus will go up by x, CN minus will go up by x. At equilibrium, 1.0 minus x, x, 1.0 plus x. Our equilibrium constant, if you recall, is rather small. It's 4.9 times 10 to the minus 10th. So we can pretty much assume that that minus x and plus x is going to be small enough to ignore. So we get Ka equals 4.9 times 10 to the minus 10th, which is equal to the 1.0, and we're going to drop the plus x times x divided by, and again over on the HCN side, we'll drop the minus x, so 1.0, and lo and behold, we get that x is equal to 4.9 times 10 to the minus 10th. Now, we don't expect this to happen every time that x is going to be equal to the Ka, but you can see how we deal with the CN minus ion. So that's the common ion that's been added to the solution that's also involved in that equilibrium. And then, of course, X is the H plus concentration, so to figure out the pH, we would take the negative log of that, 4.9 times 10 to the minus 10th, to get the pH for the value. So you can see there, though, how that common ion effect works. The next example is a little more challenging. Here we have the pH of a 1.0 liter solution of, again, 0.5 molar HCN. This time we're adding 49 grams of the sodium cyanide, and we're also adding 0.2 moles of HCl. The way we want to approach this problem is to try and eliminate the acid here. Now, how are we going to eliminate the acid? Well, first we're going to use the cyanide that's been added to neutralize that acid. So if we take that H plus that is added from the HCl and we combine it with the cyanide from the sodium cyanide that was added, we can form HCN. Right. Now we're just doing this on paper. So I've got 0.200 moles of the H plus that I've added from the HCl, and I have 1.000 moles of the CN minus, because I have 49 grams of the sodium cyanide, which would be 1 mole of that, and I've got a 1 liter solution. So 1 mole of that, and at first I'm just going to say that there's 0 of the HCN. So this is my initial. Now this isn't an ice diagram. This is just an initial and an end thing. So I'm going to react the cyanide with all of that hydrogen. Again, this won't really happen, but we can do it on paper. So this is going to go to 0. The cyanide will go down to 0.800 moles. And the HCN is going to increase by 0.200 moles. Okay. So you can see this is purely a stoichiometry step that we're doing here. Now we're going to go ahead and write out down our equilibrium that occurs. So we've got our HCN in equilibrium with H plus CN minus. Oops. Not Cl minus. Sorry. Cn minus. And our K value for this, again, 4.9 times 10 to the minus 10th. Oh, where did that ice chart come from? All right, so we fill in our data into the ice chart. So we now have, so remember before, if we look back up at the beginning, we had 1 liter of a 0.5 molar solution of the HCN. So that means that we had 0.5 moles of the HCN. We've increased that by 0.2. So we're now going to have 0.7 moles in 1 liter. So 0.70 molar of the HCN. We now have 0 of the H plus, and the CN minus, we've got our 0.8 moles left over in 1 liter, so it'd be 0.80 molar. Now we have to assume that the addition of these things isn't going to change the volume significantly, but most of the time that's a fairly good assumption. Now we go back down again, so now it looks just like the last problem we did. This is going to go down by x plus x plus x, 0.8 plus x, x, and 0.70 minus x. All right. And then we go ahead and complete this like we would an ordinary chart. We've got our Ka, 4.9 times 10 to the negative 10th is equal to x. We'll assume that the plus x is going to be negligible, so I have just 0.80. And on the bottom, 0.70, again, drop the minus x part from that. And then we go through our steps, and x would be our H plus concentration, and then we could just figure out the negative log of that to get the H plus concentration. So you can see common ions, nothing really all that special. It just means that we have, in addition to our equilibrium, we've added another ion that participates in that equilibrium through the addition of some salt. And so that's where we get that common ion effect. Usually involves some type of stoichiometry calculation that we need to do, but that's okay. Just take the time to do it. Like in this case, we combine the hydrogen with the cyanide to add to the amount of cyanide ion in solution. Alternatively, we could have filled in the hydrogen ion concentration into the boxes, but then we would have had to do a Q statement. So either method would have worked, although I believe that we would have ended up with kind of a mess that way in terms of the plus x and minus x values. So that could have been a little tricky there.